for pre-calculus notes, section 3.5, and we are looking at exponential and logarithmic models. And we left off with you trying a problem that might have been a little challenging, and so now we'll just kind of go over that. So this time we don't have the model, but we have to get the model, and it talks about the half-life here. So when we look at this, here are things we know. Use the exponential decay model. We have 10 grams initially, and it has a half-life of 1,599 years. So what that means is, is that if A equals 10, the initial amount, y is going to equal half of that, 5, and in a time of 1,599 years. So when we put that stuff in our equation, and by the way, notice they wouldn't even have had to tell us how many grams we started with, because they say, oh, the half-life. So we could have just put in a half and think about A being 1 and Y being 1/2. Just keep that in mind as you do problems. Oops, sorry. And then putting that in, taking the ln of each side, we get that B is the ln of 1/2 over negative 1599. And then the reason I said that negative with the emphasis is because it's a negative in the formula and a negative in B. So when we do that, we get two negatives there. So then I rewrote it with a positive. And then the next question is, how much is left after 500 years? So if you want to try and see if you can get that on your calculator, go ahead and pause this, and then I'll just show you that. So here's the answer. After 500 years, there are about 8.05 grams left. And that should make sense, if you kind of think about the half-life being 1,599 years. So next is the Gaussian model, and that kind of looks like that normally distributed bell curve. And if you are taking stats class, you're maybe becoming more familiar with that also, maybe by now, I'm not sure. And as mentioned at the beginning of the section, the Gaussian models are this, and in probability and statistics, this is commonly representing things that are normally distributed. The graph of the Gaussian model is called the bell-shaped curve. Try graphing the normal distribution with a graphing utility. Can you see why it's called the bell-shaped curve? And if you want to do that, go ahead, and you'll see that it kind of looks like a bell. I would say. Anyway, moving on. For standard normal distributions, the model takes this form: y equals 1 over the square root of 2 pi times e to the negative x squared over 2. The average value of the population can be found from the bell-shaped curve by observing where the maximum y value of the function occurs. The x value corresponding to the maximum y represents the average value of the independent variable. In this case, that's x. So then number 4, our problem that we're going to look at, says in 2011, the SAT mathematics scores for high school graduates in the United States roughly followed the normal distribution given by y equals, so they're giving us the model, 0.0034 e to the negative parentheses x minus 514 in parentheses squared divided by 27,378, with 200 less than or equal to x, which is less than or equal to 800. X is the SAT score in mathematics, and sketch the graph of the function, and from the graph estimate the average SAT mathematics score. So I do have that for you in a graphical form, and kind of think about what is going to happen there. And here is the graph. And it says the graph of the function is shown, and from the graph you can estimate that the average mathematics score for high school graduates in 2011 was 514. And again, if you want to try that on your graphing calculator, go right ahead. And then our next one is the logistic growth model. And this is where, you know, it's kind of exponential growth, but it isn't going to grow without bound. Maybe there are parameters that are going to keep that exponential growth from surpassing some value. And so, you know, a common example is like, you know, wolves on an island, and, you know, their population can't grow indefinitely, exponentially, because, you know, an island only has so much space on it. And so at some point, it has to kind of level off, so to speak, as we go. And that's why, you know, humankind, whatever you call it, um, as we tamper with the natural order of things, you know, we have to then kind of, there's repercussions for that in some of these populations and things like that. So that's enough of that. Moving on. So some populations initially, the rapid growth following by a declining growth rate. And here's a picture of a logistics curve. And I'm just gonna write it again over here. So y equals a over um, 1 plus b times e to the negative rx. And that is also going to be a situation where y equals a is an asymptote. So that's a horizontal asymptote, and x is time, and y is population. In this instance. So that's kind of what we're looking at, and it has a unique name. I love this name. The logistics curve is also called a sigmoidal curve, and so fun terminology. And you know, you just, as you learn more and more mathematics, you just want to have some terminology under your belt, so that you know what people are talking about in those situations. An example of a bacteria culture that is initially allowed to grow under ideal conditions, then less favorable conditions that inhibit growth, would be a logistic curve called a sigmoidal curve. So let's apply this to a problem here. And for this one, it says, on a college campus of 5,000 students, one student returns from vacation. Wow, you know, never mind. Just kind of reminds me of our world right now. Returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this. And, you know, don't you think Johns Hopkins has all kinds of models that they're using as they project how things are going with this COVID virus. But anyway, the spread of the virus is modeled by y equals 5,000 over 1 plus 4,999 times e to the negative 0.8 t, where t is greater than or equals 0, where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. How many students are infected after 5 days? After how many days will the college cancel classes, and after how many days are 250 people infected? So, you know, if you feel like you want to pause this and try that, go ahead. I am actually just going to work through it. I'm not going to pause it, work through it, and then show it to you. So for this one, I have my model, and I'm just going to start way up here on the right. So this is number 5, and my model is y equals 5,000 over 1 plus 4,999 e to the negative 0.8 t. T is greater than or equal to 0. And so I'll just color code these problems parts. A, how many students are affected after 5 days? So that means T equals 5, and Y equals 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. So that one is, pretty straightforward. Find y if you haven't already, and you should end up with about 54 people is what I got for that one. So again, a little tricky typing all that in and getting a correct answer. So by all means, make sure you're checking things as you go here. And then for letter B, after how many days will the college cancel the classes? And that means they have to have a 40% infection rate. And so we have to know how many people would be infected. So it would be 40% of the 5,000 students, and so 0.4 times 5,000, which is 2,000. So if 2,000 students are infected, they'll cancel it. So that's y, which equals y, and we have to find t. And again, if you want to pause it part by part, go ahead. And so in this one, we get 2,000 equals 5,000 over 1 plus 4,999 e to the negative 0.8 t. And so then for this one, I personally would multiply both sides by that denominator, and then I would actually at the same time divide by 2,000. And so I'll maybe write that here. So I'm going to multiply by 1 plus 4,999 e to the negative 0.8 t. And at the same time, I'm going to divide by 2,000. And you'll see what happens there. Then I'm multiplying by 1 plus 4,999 e to the negative 0.8 t all over 2,000. So that makes my 2,000s cancel here, and this stuff cancel there. So I get 1 plus 4,999 e to the negative 0.8 t equals, and then this will just be 5,000 over 2,000. 5,000 over 2,000, which is 5 over 2 as we look at that. Darn, I just made a big mistake because I've been using 5,000. They would all be affected for that. Because I'm like, wait, that's not the right value here. So I am just going to use, I'll just use black here. Oops. And I'm going to change my 5,000 to 2,000 because that's really, no, just kidding. That's not right either. Hang on, let me look. Oh, goodness. Everything is right so far. My apologies for having a little moment there. And so that's 5 halves. And so then I get 1 plus 4,999 e to the negative 0.8 t equals 5 halves. And then I'm going to subtract 1 from each side. And 5 halves is like 2.5 minus 1 is 1.5, so it'll be 3 halves. And so this will be 4,999 e to the negative 0.8 t, excuse me, equals 3 halves. And then I'm going to multiply by 1 over 4,999 times 1 over 4,999. And then I'll get e to the negative 0.8 t equals whatever that turns out to be. So that's 3 over 9,998. And then we're going to take the ln of each side. And so the ln of this and the ln of that. and the ln of each, the negative 0.8 t equals the ln of 3 over 998. And on the left-hand side, we get negative 0.8 t equals the right-hand side just as is, ln of 3 over 9998. Dividing by that negative 0.8, and I'm not going to get a fraction or anything, so I'll just write it like this, negative 0.8. I know that doesn't actually look like great form, but we're just typing that in on the calculator. See what you get. T is approximately what? And when I figured that out, I got about in 10 days. So in 10 days, they're going to have canceling of classes for that one. And that was letter B. And then for letter C, it says after how many days are 250 people infected? And, so let's estimate that. I would say if 54 people are infected after 5 days, and it's going to take 10 days to shut down with 2,000 cases, where is that going to leave us? And so that's a lot like B. Go ahead and try and see if you can do this one yourself and see what happens. So let's see how you did. Oops, just a second. There we go. I put 250 in for Y and got it down to e to the negative 0.8 t, ln of each side, and then divide by negative 0.8, and it should be about 7 days for that one. Our next model is logarithmic growth, our logarithmic models. And so then for these, we're going to talk about the Richter scale and earthquakes. And so R equals the log of I over I sub 0, where I sub 0 is 1, is the minimum intensity used for comparison. And we want to find the intensity of these earthquakes that are listed here. And I'm going to move B over so that I can use my space. Okay, and so let's look at this, and we'll look at, A together, and then you can maybe try B. These are not as long as some of these problems we've looked at. So Alaska in 2012, R was 4.0, and so capital R equals the log of capital I over I sub 0. So 4 equals the log, and we said I sub 0 is 1, the log of I. And this is a plain logarithm, so it's a common logarithm, and so our base is 10, and so we're going to do that exponentiating. Oh, we haven't done that for a while, so fun. If 4 is equal to the log of I, then 10 to the 4 is equal to, 10 to the 4, 4 is equal to 10 to the log of I. And then when we kind of keep going with that, that's 10 to the 4th equals I. And so 1, 2, 3, 4. So I equals 10,000 for the intensity there. And Church Christ New Zealand, go ahead and find that one, and we'll see how that goes for you. So let's see how that worked out. For this one, we have that same formula, exponentiating using 10 as the base, and we get 2 million as the intensity. So notice how different that is from 4 to 6.3. And, that's the kind of tricky thing about earthquakes is that intensity is exponential as we look at that, or actually, logarithmic. Sorry. And so Note that, increasing by 2.3 units is increasing by a factor of 200. And so the Church Christ earthquake was about 200 times as great as the earthquake in Alaska. And I think sometimes people don't realize that in that Richter scale. So exponential and logarithmic models, a big lesson here. And we need to recognize the 5 most common types of models involving exponential and logarithmic functions. Use exponential growth and decay, Gaussian functions, and logistic growth functions, and logarithmic functions to model and solve real-life problems. And so that concludes notes for 3.5 exponential and logarithmic models. Have a wonderful rest of your day.